Okay, hello. So last time we have talked about the effect that can change the shape of the wedge group, right? So hydrogen bonding is one of the most important factors that can influence the shape of the wedge functional group. Today we will have another examples about the so-called labile protons. So we are going to talk about the absorption of amines. So we have two different kinds. In this case, they are symmetrical and asymmetrical absorptions, or asymmetrical stretchings. So there is one other factors besides hydrogen bonding that can influence the shape of the signals. So let's consider the difference in the shape of the NH signals of a primary and a secondary amines. So if you remember, so I think you are taking the course, the organic chemistry 3 courses given by Dr. Huan, right? So I think you have just talked about structures and properties of amines. So I hope that you still remember what primary and secondary amines are. So there is actually difference between the shape of the NH group of these two kinds of amines. So this is the infrared spectrums, typical infrared spectrums of a primary amines. In this case, it is hexyl amine. And you see that we have a typical absorptions for primary amines. It is in these regions. And then you have the typical examples for secondary amines. In this case, you have piperidine, and the absorption of the NH group quite different from that of the primary amines. So what is the difference? So the primary amines exhibits two signals at this range. One is at 3,350 centimeters to the -1, and the second is next to it, about 100 centimeters away, so about 3,450 centimeters to the -1. So you have two peaks. We say in this case we have two spikes. Two spike. And in case of secondary amines, you see only one signals. It looks a little bit broader, a little bit wider than the signals of primary amines. So what is the reason for this? So the first explanation may come from the fact that the primary amines, the primary amine has two NH signals, and these two NH signals will give two different signals. Sorry, two NH bonds, and these two NH bonds will give two different signals. And so you see two spikes in the infrared spectrum of primary amines. But this obviously that secondary amine has only one NH bond, so it should give only one signal. But in fact, this explanation is not really satisfactory. We have a better way to explain for the different of numbers of peaks in absorption of secondary and primary amines. So in fact, both NH bond of a single molecule will together produce only one signal. Hai liên kết NH thì tạo ra một tín hiệu thôi. Because they are actually the same. They're actually identical. But these two NH bond can have different vibration at the same time. So two NH bond can have two possible vibration at one moment, and this will produce two signals. So you see the pictures on the right that show you one way of vibrations. It is symmetric stretching là kéo giãn, and in this case the two NH bonds stretch at the same time, to the two directions. This is called symmetric stretchings. And you also have asymmetric stretchings. So in this case, the NH bond on the, okay, I should make some notes. So in this case, you see that both of the NH become longer at the same time and become shorter, of course, at the same time. So you have symmetric stretching. Okay, but on the second pictures, you see that the NH bond, okay, this is a nitrogen, this is a hydrogen, so nitrogen, and the NH on the right become longer. It is stretch. No, sorry, it's become shorter. Sorry. This one becomes shorter. And the one on the left become longer. The one on the right become crushed. And the one on the left become stretch. So in this case, you have asymmetric stretchings. And symmetrics and asymmetrics motions will produce two different signals. And therefore, at any given moment, approximately half of the molecule will be vibrating symmetrically and half will be vibrating asymmetrically. And you see, and therefore you see two different peaks that are close to each other and in the range of the absorption of the NH. So one of the signals is produced by half of the molecules, and one signal is produced by the other half. So you see that you have two similar peaks. So for the same reasons, the CH bond of a methyl group normally appears just below 3000. Also give rise to a series of signals, and these signals also corresponding to symmetrics and asymmetrics vibration or stretchings. So the reason for the appearance of different peaks corresponding to just one kind of bonds may due to the asymmetric and symmetric vibrations. So you can see this in the following spectrums. Okay, so we have a small practicing exercise. In the following infrared spectrums may correspond to a ketone, alcohol, a carboxylic acid, a primary amine, or a secondary amine. So please try to guess if these spectrums corresponding to which kind of functional. So you have the first examples here. So if you remember, we care about the regions on the left of 1500. The right is a fingerprint with a lot of signals, and you cannot. Secondary amines, yes, maybe. Yes, if it is a secondary amine, then you should see just one signals as about 3000. Yeah, I come back to the previous slide. Maybe we will analyze it. I think at about one signals. I think this kind of signal can be said to be weak or medium. Yeah, better is medium. It's not so weak. It's look quite big. So I think this is about 3000. Yeah, 300 to 3400. Some about. You don't have to be exact at that. Okay, so fingerprint we don't have to remember because it has so many signals. We just consider the range above, and then you have to draw a line at 3000 to see if you have a double bond or triple bond. I think in this case you have only signals just below 3000. So and you see three peaks, 1, 2, 3, and they corresponding to symmetric and asymmetric vibration or stretchings of CsP3H. So this one is a saturated compound, and a very strong and prominent signals in the range of about, here is 1700, and I think our signals is just above, a little bit above. Yeah, I think about 1720 something, yeah, and strong. Yeah. And I think it could be sharp. So positions, intensity, and shape, then you can come to the conclusions. Okay, let's have a look. Yes, this I think it should be a ketone, actually. Yeah, someone said it. Yeah, it's. I think it is a ketone. I think this should be a ketone. And actually, that has a reason to say that it might be a secondary amine because you see a small peaks here. And if you remember, this is actually not a noise. It is actually a peak corresponding to our compound. Cái này không phải là iốt mà nó là một cái peak thật. Yeah, I think it's about Tú said it's 3,450 about. Yeah, so this is actually 2 times of the wave number of ketones. Yeah, we say it is overtone, and actually this is not so. Yeah, we don't have to care about such typical things. This could be water. This could be water vapors that has been absorbed into your sample when you carry out the measurements. Because as you remember, when you measure infrared spectrum, you have to put the samples between 2 solid plates. Yeah? Solid plates, solid in this case could be potassium bromide, and it is very water sensitive. It absorbs waters, and so it might produce the absorption at about 3,600 corresponding to the OH group. So I would say that this one is a ketone, and more detail, it would be saturated ketone, because you don't see a double bond, CC double bond in this case, a triple bond. Okay. This one looks quite typical, right? So yeah, 3,000. Yeah, I agree. Yeah. I think it is an acid that had a very fast answers. So remember that it is has a very broad and typical. Yes, it is carboxylic acid. I agree. So this rate is from 3 to about 2 rods, and in this range, if you remember, is the OH. With hot H bonding, and of course this is also CsP3H. It is overlapped by the broad signal of the OH, and here is strong and typical for the absorption of the carbonyl group. So it is actually we cannot say it is saturated or not, because this rate is it is actually saturated because you don't see no signals for CC double bonds. So in this case we are not sure if we have Yeah, CsP2H, but we don't see CC double bond. So I think it's also a saturated. That's it. That's right. Okay, this one looks complicated. Okay, no signals for, yeah, secondary amine. Someone has a request answer, so no signal for double bond in general. No CO, no CC double bond. And yeah, you see just below 3000 several peaks, and they corresponding to CsP3H. Asymmetric and symmetric. And yes, the most important signals in this spectrum is for, I think it's about 3,000, 3,280 maybe. And it looks a little bit broad. Yeah? It looks a little bit broader than those of CH because NH can also form hydrogen bonding, but not as strong as alcohol, so just a little bit broad. And you see only one signal, one peak, and in this case it should be a saturated secondary amine with just one NH bond. The saturated secondary amine. Okay. What is this? So you see that I always pay my attention to the range of double bonds. Yep, primary amine, thank you. So I always pay my attention first to the range for double bond because it's maybe the most important range. So in this case, nodes, signals for double bond in general. $1,500, and we just look up here, and it is for CsP3H, two kinds, symmetric and asymmetric. Okay, again, the most important signals, the two most important signals that are close to each other. So this one is 3,350. This one 100 centimeters above. So yes, they are the signal for primary amines. So this is saturated primary amine. Yeah, it has two NH bonds, and these two NH bonds can stretch symmetrically or asymmetrically. Yes. What is this? So what I'm looking for are cues. Yes. Yes. Ketone. Thank you.
Thầy chỉ bảo em là em đi sâu thôi, trả lời học học dễ.
So I would say 1,000.
Thầy hỏi em là tại sao em không thuộc bài thì em không lý do đấy.
1,720s.
Thầy hỏi em là
And
thầy có nói trong cái
sharp
em có
and
nói
strong.
em nói xong
So
thì
it
thầy nói
is typically for CO double bond, CO double bond, not for CC double bond, because CC double bond will have a weak absorption. So this is for, you know already,
đấy, thầy có nói gì không? Thầy hỏi em.
3H, two different kinds, symmetric and symmetric. And this is the overtone
air relationship.
of the carbonyl group. And actually you don't have to talk about this overtone. So a saturated ketone. Yeah. So this, yeah, alcohol, thank you. So no signals for double bond. These are the absorptions of CsP3H just below 3000, two different kinds, symmetric and symmetric. And you see a broad, not as broad as the OH of carboxylic acid, from 3,600 to margin body. So this is an saturated alcohol. Okay. This is simple. It's due to symmetrical and asymmetrical stretchings only. Okay. Now we go to the final part of these sections, how to systematically analyze an infrared spectrum. You should go step by step. You can also do it as you have successfully did as before, but actually we have some steps that we can follow to make our analysis more systematic. So you have the summary, the table summary, all the absorptions of the most common functional group. So I think now you have more or less remember all of this. So I think we should go through this very fast. So I think one of the signals that we have not talked much about is this one, the aldehyde. The aldehyde contain a CsP2 hybridized H bond. CsP2 H bond, but it's absorbed much lower. It's much lower than the CsP 2H of an alkene, and the explanation is quite interesting. If someone interested, we can discuss later. Quite interesting explanation for this difference. Okay, and then you have a double bond, a triple bond, and then double bond regions. Okay. For fingerprint, really we will not talk about this. So when you analyze an infrared spectrum, the first step is to locate the 1,500 centimeters positions, and then we just focus on those signals that are found on the left of this line. We call this its diagnostic regions. And then you have some useful informations. The first region that we concerned about is the region for double bond. So double bond is ranging from 1,600 to 1,850. And then you have the range for triple bond, so CC triple bond or CN triple bond, and it's about 2,100 to 2,300, a little bit higher, because triple bond is stronger than double bond. Okay, the last regions have more signals. In this region you have hydrogens, you have bonds that is made from hydrogen and one other atoms like carbons or oxygen or nitrogens. And it covers quite a wide range. And you should remember that each signals will have three parameters. Wave numbers tell you about the locations, and intensity tell you about how strong or how big the signal is, and the shape can be either sharp or broad, sharp or narrow or wide. So you can see the range of the XH bonds, just below 3,000 CsP3H, just above 3,000 CsP2H, and then CsPH. And if you go further, you can find the signal for NH. Remember, primary and secondary will have different sites, and then OH always produce, not always, often produce broad signals and strong due to hydrogen bonding. Often, not always. Okay, now you have a compound with a molecular formula of C6H10O. And now we will go through steps that help you to deduce the structures of this compound. We go step by step. Đây là chúng ta nói lại cách hướng còn sau chúng ta sẽ tự chúng ta làm tự chúng ta. Okay, and in this case, the spectrum gives you the exact numbers. You don't have to guess. Two most important signals are at the double bond regions. So identify the structures below that is most consistent with the spectrums. So you see that in our spectrum you have, this one is for C carbonyl group, and this one is for an alkene. And in all of our compounds, you see that some compounds you see only CC double bonds. Some have both CC double bond and carbonyl, and some has only carbonyl. and some do not have any double bonds. So you can very fast exclude those that do not have two double bonds. So this one will not corresponding to the spectrums. Yeah, triple bond we don't have. So we have three potential candidates in this case. Not this one. Two only. Yeah. We have only two potential candidates, and they both have signals for CO and CC double bonds. And now we go further to decide which one is corresponding to the spectrum. So as we talk about, we will draw a line at 1500, and we then find the signals on the left of this line. So on the left you see 1650 and 1720. 1750 corresponding to CC double bond, and triple bond we don't have anything, and double bond you have two important signals corresponding to CC and CO double bond. No signal in the triple bond region. Okay. So this is a CO, this is a CC. But now you have to decide if they are next to each other or they are isolated, the two double bonds. Okay, just above and just below 3000, you see signals for CSP2, and here you have CSP3H. So you now you draw a line at 3000. And look for signals on the left and on the right of the line. You have just above 3000, so it corresponding to Vinilic CH. So this information is in a good agreement with the fact that you have a CC double bond. Remember that if you have a CC double bond, it does not mean that you always have CSP2H, because the substituted CC double bond will not have CSP2. Okay, if you go further, you will not see signals for OH and NH. This one is actually overturned on CO, so we don't have to care about this one. Because if you have OH or NH, then the intensity will be medium to strong, and it is not it's not as weak as these signals. Yeah, as I told you, it is the tone of CO double bond. Pump, they call it pump. Yeah, so the diagnostic regions provide the information necessary to solve these problems. So our compound should have C double bond, CO double bond, and also CsP2H. And among those structures, you can choose two most potential compounds. They both have the all the characteristics that we have analyzed, but they are different in the structures. So the first one, this one is conjugated. Because carbonyl group and C0 bond are one bond separated, and they are this one not conjugated. Because they are so far away from each other, so 1, 2, 3 bonds apart. So no conjugations between the two double bonds. So to distinguish between these two compounds, you have to pay attention on this difference. So you have learned that unsaturated and isolated ketones will absorb at higher wave number. This means that it's saturated or not conjugated ketones. Will absorb at larger wave number than conjugated ketones. So this conjugated ketones, and you still remember, I hope, the two numbers. Ví dụ đi thi mà chúng ta nhớ được chỗ này là có nối đôi CC, thì bạn này được 1 điểm. Chúng ta nhớ được là nó có nối đôi CC này, nó có nối đôi CO này, nó có CHSP2 này, thì mình đã được 0,75 rồi. Nếu mà chúng ta tìm ra nó là liên hợp hoặc nó là không liên hợp thì sẽ được chọn lại 1 điểm. Ví dụ như vậy. Chúng ta cứ làm khi mà phân tích phổ thì người ta không quan trọng cái chuyện là chúng ta có tìm ra cái cấu trúc chính xác của cùng hay không, và chúng ta phân tích các đặc điểm trên phổ đó, và mỗi đặc điểm suy ra một loại nhắm chức, thế là được điểm rồi, nó sẽ có điểm rồi, chúng không cần phải tìm ra cái chất hoàn chỉnh này. So in the spectrum provided, the carbonyl appears at 1,720 centimeters to the -1. So this spectrum corresponding to a not conjugated ketones. So this one is the structures that we are looking for. Okay. Đây là ví dụ của chúng ta làm. Thi cũng chỉ như thế này thôi. Okay, match each compound with the appropriate influence spectrum. Đây chúng ta sẽ làm nhanh được không? Oops. Đây chúng ta sẽ làm nhanh nhé. Chúng ta sẽ không nói chi tiết được không? Để chúng ta nói từ từ vậy. Yes, I agree. This is alkene. Okay, some people may need more information, so I will go slowly. So this should be signal for CsP2H, and this is for CsP3H, and no signal at yes, you have weak. I don't know the exact numbers. I think it will be about or just above . And this case, we say it is sharp and it is weak, so it is not a carbonyl group. It is this signal for CC double bond. Yeah, so it's in good agreement with the CsP2H. So just to simply tell you about alkene. Okay, you have only one structures here, one alkene in this case. Thank you. And you see that the intensity of CsP3H, the intensity of the signal for CsP3H is strong. And it is weak. Why? Because here you have only three CH bonds, CsP3H bonds. But you have a greater number of CsP3H. Yeah? You have a lot of CsP3H here, and therefore the large number of bonding CsP3H bond contribute to the strong absorptions. So weak, strong, weak. Okay, right. Okay, this one. So this one should be a ketone, I guess. Yes, people very fast. Yep. Strong and it's strong. So carbonyl. What is that? In this case, we have not 20, but maybe 40. Not the ketones. Actually, we have an esters. Yeah. This one. Yeah, I think esters better. Esters better because you have 1,000 a little bit higher than ketone, right? And you don't have CsP2H, so saturated esters. Okay, so spectrum C. So this one we have, yeah, not so many informations, not so many information indicated, and yeah, agree, alkane, agree, yeah, only sp3H. Okay. Ui. What is this? What is this? Alcohol. Do we have alcohol? Yeah, we have alcohol, right? So the only alcohol we have in this case is this one. This is just OH. Always remember the three parameters of one signal. Location, wave numbers, strong or weak, intensities, and shape, broad or sharp. So alcohol in this case is the best answer. Ui. What is this? Ketones? Yeah, maybe acid, right? Acid may be better answers. Yeah, this is broad, very broad. From here to here, and this is carbonyl. And actually you see two carbonyl group. Yeah? You see two signals for the carbonyl. Actually, you see two. Yeah? So I have to make it. So this is one peak, and this is second peak. Both are very strong. They're very close to each other. And I guess here you have CO and CO. But the first one corresponding to free carbonyl, and this is for carbonyl with hydrogen bonding. Yeah, it's okay, doesn't matter. Yeah, so I think we have two, in this case we have two signals for two kind of carbonyl. In this case, actually the two carbonyl are the same, but sometimes one carbonyl is free, and sometimes it becomes a little bit weaker by hydrogen bonding. So you have to see two signals at this range. Vậy là đây có hai cái nhóm carbonyl nhé. Đầu tiên mình thấy đúng không? Vì là cái này nó không phải là một cái alkene, không phải là một cái ứng với alkene, không phải ứng với carbonyl. Cả hai đều là carbonyl cả. Alkene nó không mạnh như này đúng không? Và alkene cũng không cao như này. Đây là do nhóm axit nó lithium và axit tự do. Okay. Yeah. What is this? Yep. Amines, and more concrete, it is a primary amine because you see two peaks, two spike. So corresponding to the absorption of primary amine with asymmetric and symmetric vibration. So the last structures. Both of these are the last structures. Okay. Để làm một chút nhé. Bây giờ làm khoảng 10 phút.
Hãy có tình yêu cho lòng nặng em nắm say 3 năm 6 8 10 đủ rồi nha.
Okay, let's continue. So one application of infrared spectrum is to distinguish two compounds. So you can use infrared spectroscopy to differentiate two different compounds. And this is very useful when you perform reactions in which a functional group is converted into another functional group. So, for examples, if you have an alcohol and you are going to oxidize this with oxidizing reagents, what is the suitable oxidizing reagent in this case? What is the oxidizing reagent in this case to produce a ketone? If I want to have a ketones, which oxidizing reagent should I use? DMSOs? Yeah. Not enough. So if you want to oxidize an alcohol to carbonyl group, please don't use copper oxide. Yeah, please don't do this one because it's funny. People will not do that. Chemists will not do that. Instead, they will use what I said, sworn oxidations. So in this case, you have to use three components: oxalate chloride, that said, DMSOs, and you have triethylamines. So this is one way sworn oxidations, or you can use Dess-Martin's carryogenant. So you can use this one. I hope that you still remember from organic chemistry 2. Or you can use PCC, Chrome, PCC is Chrome 6, but it is not so easy, so you have to use this. You should use this one. In this case, if that you and then it's too strong, or you can use pyridine with SO3. So 1, 2, 3, 4 different ways to do this experiment. I hope you still remember this from organic chemistry 2. Please don't use copper oxide. Okay, so you are quite lucky because Mr. Hian didn't teach organic chemistry 2, right? Otherwise, you have to learn so many things. You are lucky, right? Okay, so after running the reaction, it is possible to verify information of the product by looking for the absence of an OH signals and the presence of the newly formed carbonyl signals. So, in order to distinguish these two functional groups, you must remember the absorption, the typical absorption for carbonyl and for the OH functional group. Okay, so one more examples. Oops. I think I have missed some slide. Okay, I think I have by accident deleted some slide, but I hope that you understand the application of infrared spectrum in this reaction. You have two different functional groups, OH and carbonyl, and they have different signals in the infrared spectrum, so you can use infrared spectrum to distinguish to check if the reaction has happened or not. So at the beginning you have if you start the reaction and after for example 1 hour, you take a small amount of your mixtures of the reaction mixtures and test and analyze it with infrared spectrum. And of course, you still see some signals of OH because the reaction has not yet been completed. But after 1 more hours, you take another drops of your reaction and analyze it with infrared spectrum. You may notice that the signals for OH at broad signals at 300, 600 and to 200 has been disappeared, and instead you see a new signals at 1700 ketones. So you know that the reaction has been completed and it is successful because you see the desired product. That is the infrared spectrum application in this case, applied in this case. Okay, identify how infrared spectrums might be used to monitor these reactions. So first you have a terminal alkene. First you see a terminal alkene. And then you have a substituted alkenes. And then you can use infrared spectrum to distinguish these two compounds. So first you compare the structures of starting materials and starting materials at O. And this is product. And then recognize the functional groups in starting materials and in products, and then you go through the various reagents of the spectrum and look if you can see any difference in each region. Okay, so we begin with the region of the double bond absorptions. So you see that starting materials and products both have C double bond, but they will have different intensities. The reactant has an unsymmetrical carbonyl C double bond, while the product has a symmetrical C double bond. I hope that you still remember this part. So this C double bond of the product of the reactant is not symmetrical. So the red carbon is bonded to 2 alkyl groups, and the blue one is bonded to hydrogen. So these 2 carbons will be different in terms of electronic environment. And if you remember, you have molecular dipole moment depends on the charge on each carbon and the distance between these 2 charges. And you see that because these two carbons are different, so the charge will be different from 0. And so the dipole moment of the CC double bond of the reactants, the starting materials, will be different from 0. But the product has symmetric structures. The product has a symmetric structure, so because it has two identical carbons at the double bond, these two carbons are identical. So in this case, they do not have charge at all. So they do not have dipole moment. A bond that does not have dipole moment will not absorb infrared radiations. On the other hand, a bond with a small dipole moment will produce signals. They are weak signals, but it is there at about 1650 centimeters to the minus 1. So you have a very different spectrum between the reactant and the So the drop of reactions, as I told you, a drop of the reaction mixtures can be removed from the reaction flask at period intervals and analyzed in an infrared spectrometers. As the products forms the signals at 1650 centimeters should disappear. I think this point is not really exact. I would say that when all the reactants or starting materials
Cái áo của em lưu cay này.
Ở đâu?
Cái áo mà bé Habit đấy, màu xanh xanh lá. Chị mặc áo chị mặc đúng rồi. Chị để đúng.
or has been
Hợp cái.
Không nhớ tí tìm nhá.
converted,
Bây em mặc gì đi?
then the signals, its signals will disappear. Khi mà chúng ta mới thực hiện phản ứng thì nó không thể nào mà nó hoàn toàn, đúng không? Nó vẫn còn chiếc đầu và có một chút sản phẩm hình thành thì không thể có chuyện là cái tín hiệu của carbon nối đôi không nối xuống chiếc đầu nó biến mất hoàn toàn được. Nó phải biến mất, nó chỉ biến mất hoàn toàn khi mà tất cả chất phản ứng ban đầu đã chuyển hóa. Okay, so let's consider the reagents containing signals from the XH bonds. So this is the starting materials, and it has the carbons still had hydrogens bonded to it. So this you have absorption signals corresponding to CSD2H at about 3100. This tells you that you have a vinylic hydrogen. It is vinylic hydrogen. But in the product, you have a tetra-substituted double bond. And tetra-substituted means no CSD2H. So of course you will not see So this difference can also be used to distinguish between the starting materials and products. When all the starting materials has been converted to the products, then the signals at 3100 will disappear completely. So during the reaction, you may see the change in the intensity of these signals, I would say. So during the reaction, we can notice the decrease I hope that you still remember how to draw the reaction mechanism that converts this double bond to this double bond. I hope you still remember the reaction mechanisms. Okay, so two differences. The first difference is in the range of the double bond, and the second difference is in the range of the CsP2H bonds. So now you have the real pictures of these two compounds. The first one corresponds to the starting materials. So you see that this is the starting materials. You see that you have CsP2H, this CsP2H, and this is C0 bond, and asymmetric C0 bond. And the infrared spectrum of the product have different structures. So the product is the tetrasubstituted alkene. So you have two methyl groups. So in this way, you see that the signals of CsP2H has been disappears, and also you don't have signals for C0 bond, even though you have it in your structures, because this one is symmetric. Symmetric bonds in general will not absorb infrared radiation or infrared light in general. Yeah. So you can use infrared spectrum to efficiently distinguish two compounds. In this case, first one is starting materials, and the second one is product. Okay, sorry. Okay, so I think we will go through this exercise very fast so that we know how to use infrared spectrum to distinguish between the starting materials and products. So in the first reaction, you have an alcohol, a primary alcohol, and it should have a broad so it will have OH and in your product, which is carboxylic acid, then you will also observe OH. But it's OH acid, and this is broader. Very broad and strong. And in addition, you have carbonyl or carboxylic acid at about strong and sharp. Okay, for question B, this is for question A. So question B, double bond does not change. So we just pay attention to NH. So this is a secondary. So you have NH secondary at about, I would say, something between this range, and you don't have NH anymore. In this case, in C, you have triple bond. You reduce this with a catalyst, and then you have a double bond. So triple bond will have a signal at about 2100. I think it is weak and sharp. Why the product you have C triple bond? 1600, maybe a little bit smaller because it is conjugated. Yeah, the same for CMB and the same. No. It is different from CMB because we don't have signal for double bond and triple bond. Actually, we cannot base on the signal of double bond and triple bond to differentiate between those signals. So we cannot base on this. Yeah, so we have to base on conjugate. But actually both are conjugate. Yeah, it is difficult. Both are conjugate. Both are conjugate. So I think it is quite simple to distinguish between the triple bond and double bond is the so-called vinylic H. So in the product you have two vinylic protons. So you will observe the absorptions for CsP2H at about 3100. So remember, in this case, both compounds are conjugates, and so the signal of carbonyl may be very similar. And triple bond and double bond are symmetric, so they will not produce signals in infrared spectrum. So we cannot base on double bond and triple bond, but we can base on the CsP2H, I think. Okay, the last one, I think we can base on the difference between conjugate and not conjugate, unconjugate. And this is not conjugate, not. Or you can base on the signal of double bonds. It would be smaller than 1650 because it is conjugate, and in drug product you don't have a double bond again anymore. It is converted to CC single bond, so you cannot see the signal from double bond. You can base on two information: conjugate carbonyl, not conjugate carbonyl, or you can base on the disappearance of the CC double bonds when you reduce this one. Okay, I think it is enough for infrared spectrum. Cái phổ ngoại thế là mình cũng tạm rồi. Sau này khi mà mình học hết phổ khối và phổ tuần nhân ấy, thì lúc đó mình sẽ luyện tập những cái loại bài mà nó gồm có cả ba phổ luôn, cả phổ ngoại, phổ tuần nhân và phổ khối, cho nên lúc đấy mình sẽ quay lại mình luyện tập phổ ngoại tiếp, chứ không phải là chúng ta sẽ dừng hoàn toàn, đúng không? Thế thì vẫn còn thời gian thì chúng ta sẽ nói một chút, nó sẽ chuyển sang phổ khối lượng nhé. Cái bài tập này chúng ta tự làm nhé.
谁若问的深切会逍遥，爱因我的谁你寻找。
Chúng ta như thầy nói là chúng ta sẽ còn luyện tập cái phổ tổng hợp luôn đấy, tức là có cả một chất mà chúng ta sẽ phải dùng cả phổ ngoại này, cả phổ khối, cả phổ hữu nhân, thậm chí cả phổ UV nữa. Thì lúc đấy cái loại bài tập đấy sẽ giúp mình ôn lại tất cả các phổ ngoại, thì như thế là tương đối nhiều, ba buổi hơi nhiều. Okay. So I will turn off this slide and switch to the mass spectrometries. Okay, can you see the slide for mass spectrometry? Okay, thank you. So very fast introductions. So at the beginning of these chapters, we define spectroscopy as a study of interactions between metals and electromagnetic radiations. Vậy phổ cái chữ spectroscopy là dùng cho phổ ngoại này, phổ của tuần nhân và phổ UV, nhưng với phổ khối thì lại dùng là spectrometry. So in contrast, mass spectrometry is the study of interactions between matters and an energy source other than electromagnetic radiations. Như vậy là khi mà thay một cái nguồn khác thì nó không còn là spectroscopy nữa, mà là spectrometry. Vẫn gọi là phổ, nhưng mà cái thực tế là bản chất nó khác nhau hoàn toàn. Okay, mass spectrometry is used to determine the molecular weight and molecular formula of a compound. Cái này hôm trước hôm thi học kỳ 1 đấy, khi thi hữu cơ 1 đấy, thì thầy có không dạy một tí nào cả đúng không? Thầy có bảo với bạn là hôm thi mình là chất gì này? Hôm thi của mình là chất hôm ta thi học kỳ 1 đấy, là thi cái chất này đúng không?
Như hôm đấy là khối lượng 72 hay sao ấy.
Đúng rồi. Tức là thầy chỉ bảo là các em tìm, người ta cho công thức phân tử của cái này rồi đúng không? Sau đó là các em tìm trên cái khối lượng là mấy cái này đúng không? Tìm cái chỗ mà có số 72 ấy, quanh vào thế là được 1/4 điểm, không phải làm gì cả đúng không? Thế thì cái hôm cái chất này hôm mình đi thi là chất này đúng không? Ở cái hôm mà thầy dạy ở trên lớp ấy, thì có lấy ví dụ là chất này. Thực ra về phổ cái chất này là nó gần như giống nhau. Nếu mà vẽ phổ ra nó giống phổ tự nhiên là nó giống nhau hoàn toàn luôn, chỉ khác một chút về cái độ truyền dịch học của cái carbon như này thôi. Và khi vẽ phổ ra là nó giống nhau, nhưng là hôm đấy chúng ta không học phổ gì đấy. Không, bởi vì thực ra không, cái câu 1 nó đã quá khủng khiếp rồi đúng không? Cái câu 1 nó quá là nhiều thứ rồi, bây giờ lại học phổ kiểu chi tiết như này nữa thì thầy cũng không thể nào mà chịu nổi đúng không? Okay, so mass spectrometry is used to determine molecular weight and molecular formulas. The principle is your compound with samples is first vaporized and converted into ions, which are then separated and detected. Cái sample của mình có thể là gas sẵn rồi, nó có thể là liquid, nó có thể là solid. Then liquid or solid samples will first be vaporized and then converted into ions. And now we will see how it is converted to ions. The most common ionization techniques involve bombarding your compound with high energy electrons. Vậy là trong trường này chúng ta không dùng ánh sáng nữa, chúng ta dùng một cái chùm electron có năng lượng cao để chúng ta bắn phá cái phân tử chất của chúng ta. Như vậy thì cái phương pháp này cũng khác với phổ ngoại và khác với phổ tự nhiên. Ở chỗ là cái phân tử sau khi được phân tích bằng phổ khối lượng thì nó không còn nguyên vẹn nữa, nó bị phá vỡ. Còn các cái samples chúng ta đo UV, NMR thì nó sẽ được bảo toàn. Đấy là cái sự khác biệt lớn giữa các cái phương pháp. So these high energy electrons carry an extraordinary amount of energies, and it will then ionize the compound. It will take one electrons from your compounds. Như vậy là trong trường này người ta thấy cái chất, cái ví dụ này người ta có các lý kết đơn đúng không? Người ta hình dung là các lý kết đơn thì sẽ được hình thành do dùng chung của các cặp e hóa trị. Và thấy ví dụ như vậy. Thế thì khi mà cái phân tử này nó va chạm với chùm electron năng lượng cao đấy, thì một trong những electron của các liên kết này nó bị văng ra ngoài. Có nhìn không? Ví dụ cái chỗ này hạn, electron ở chỗ này hạn nó bị văng ra ngoài, và tôi đã thấy là liên kết CC nó không còn là, nó chuẩn bị đứt rồi đúng không? Nó chỉ còn một electron ở giữa thôi. Một electron thì nó bị bay ra bên ngoài rồi. Cho nên là cái phần còn lại chúng ta có tính chất, thực ra nếu mà viết một cách đầy đủ thì cái chỗ này nó phải là cộng và chấm thôi, đúng, chứ không phải là chấm không. Bởi vì cái chấm này thực ra nó không biết nó nằm ở đâu nhé, cái chỗ này là ví dụ thôi, example thôi. Và thực ra chúng ta nhìn thấy tất cả các electron ở các chỗ khác đều có thể bị văng ra ngoài khi va chạm với electron, mà cái này là random thì không có một cái chọn lọc cụ thể random thì cái chất và cái sản phẩm chúng ta thu ở đây người ta sẽ thường viết một chấm thì mới đúng, bởi vì cái chấm này nó không xác định được vị trí của nó, không xác định được vị trí. Can be at different positions. Ok, chỗ này thực cái là người ta ví dụ như vậy thôi nhé, chứ không phải là nó luôn luôn ở giữa nhé. Cái này gọi là một cái radical cation ions. Những cơ một thì mình chỉ học radical với lại carbon cation ions đúng không? Nhưng mà trong cái trường này chúng ta có một cái sản phẩm mà gọi là radical cation ions. Vâng. Okay. So when a high energy electrons strike or bombard the molecule, it causes one of the bonding electrons in the molecules to be ejected. In this technique is called electron impact ionization. Không cần phải impact được rồi, thường gọi là electron ionization thôi. Electron ionization, EI pigment. It will generate a high energy intermediate that is both radicals and cations. We call this one radical cations. Yeah, it is radical because it has an unpaired electrons, and it is also a cation because it has been lost. It has lost one electrons and become positively charged. So it is radical cations. The mass of the lost electron is very small. So compares to the mass of the molecules. So the mass of the radical cation is actually equivalent to the mass of the original molecule. The radical cations symbolized by M plus and dot gọi là is called the molecular ion, ion thứ tử. You have to remember this word, these terms. Molecular ions, or the parent. Yeah, parent ion is not so commonly used. We use molecular ions, and it is drawn as M plus and dot. Because you have an unpaired electron in this intermediate, so it is very unstable and it is going to be further fragmented. And when it is fragmented, it will generate two different fragments. So the first fragment has an unpaired electrons for radicals, and the second fragment has a positive charge for carbocations. So the total charge and electrons of the two fragments should equals to the electron and charge of radical cations. Khi mà nó đứt thành đôi nhé, thì chúng ta thấy là nó phải có tổng có thành hai mảnh đúng không? Nhưng mà tổng atom và tổng thể tích của hai cái mảnh đấy nó phải bằng cái tích atom của cái radical cations. So most commonly, one fragment carries unpaired electrons for radicals, and the second fragment is positively charged fragments for carbocations. So in this way, the ionization process generates different cations. Among those are molecular ions and carbocation fragments. And remember that molecular ions is like this, and so it is also called simply some kind of cross positively charged, and molecular ion is also positively charged. This is the figure, simplified figures for mass spectrometers. So you see that first your samples. Yes, the sample can be either liquid or solid or gas. And if it is liquid or solid, it will be heated. It will be heated to become gas, and then the vapors, the sample vapors will be bombarded by electron beams. Đây là đầu tiên cái sample của chúng ta nếu nó là rắn hoặc là lỏng phải bị đun nóng trước và nó máy hơi đã, đúng không? And then and when your sample is bombarded with high energy electrons, it will be ionized. So it is an ionizing regions, and in these regions the ions will be accelerated. So you see that radicals is not accelerated. So radical is neutral, right? Radicals are not accelerated. So actually, we should say positive ions are accelerated, and then it will goes through a strong magnetic field, and when it goes through this magnetic field, the ions will move in different directions. You see that? Different ions will move in different directions because they have different masses. Lúc này thì khi mà đi qua cái chỗ tăng tốc ấy, thì chỉ có những cái ion được tăng tốc thôi, và nó cụ thể là cả ion dương tăng tốc, còn radical thì nó không có ít tích cho nên nó không được tăng tốc, và do đó đi qua chỗ này chỉ còn là ion dương thôi, chỉ còn là ion thôi. Và bởi vì các cái mảnh chúng ta có khối lượng khác nhau cho nên nó sẽ được tăng tốc với các cái gia tốc khác nhau, và nó đi chuyển theo các hướng khác nhau, và nó đập vào cái collectors với các tín hiệu khác nhau, và từ đấy thì mình sẽ thu được thông tin về các cái cation với khối lượng khác nhau. Thì đây là chúng ta đến chỗ detectors. Đây là detector assembly. Các cái ion có khối lượng nặng nhẹ khác nhau thì nó sẽ va chạm vào nó với các vị trí và tốc độ khác nhau. Từ đó chúng ta thu được các tín hiệu tương ứng của chúng đó, chúng ta phân tích. Máy phổ sẽ tính toán dựa vào tốc độ cũng như góc va chạm để suy ra cái khối lượng chính xác của một cation. Okay, so it is now 10 to 5. I think I will stop here for today. Next time we will go further in mass spectrometries. Thôi nghỉ nhé. Okay, được. Sau chúng ta sẽ nói tiếp phần phục hồi nhé.
Dạ thầy ạ.
Ok, bye bye. Xin chào các bạn nhé. Bye bye. Bye bye, bye bye.